Hello, everyone. I think we're ready. Welcome to my talk. My name is Konstantina Christakopoulou, and today we're going to talk about recommendation under constraints. Okay, so this talk is going to be based on work that we did with another AI with the best speaker, actually, Geographical, and also my advisor, Professor Arindam Banerjee from University of Minnesota. So first of all, let's see, why do we care about recommendation? So the answer is very simple. We care about recommendation because recommendation is everywhere. You can see it in all the different companies. Like, for example, in Netflix, they recommend to you what are the most appealing movies for you to watch today. Or, for example, in YouTube, they recommend to you what's the best video that you should watch based on your browsing history and so on. Or, for example, in Amazon, they can recommend to you that these are the top 3 books that you should read based on how your friends have also read books and how your browsing behavior has been. Or, for example, every day you will choose your, let's say, your favorite news article recommendation site, and they will curate what will be the news articles that you will see based on your preferences. Or, for example, entire companies like Pandora or Spotify for music, they're basically based on this whole idea of giving this personalized playlists based on your interests. And the list goes on and on. So because of the fact that there is this growth of this more and more content which is being generated every day, like millions of news articles, new tweets, and so on, there is this need of having these systems that are able to actually provide to you the right information at the right time to the right user. So that's the main motivation for why people are interested in recommendation systems. And it's a very active research topic, but it's also a very active industry topic. So the outline of this talk is that first, I'm going to be talking to you about a lot of work that has happened in the problem of unconstrained offline recommendation. And I'm going to tell you in a second what I mean by that. And then I'm going to be talking about 2 different types of constraints that appear in real world recommendation data. So first of all, about recommendation systems, a very popular approach which has been established in the industry and in academia, has been the latent factor-based approach. So what this says is that basically you have this matrix of how different users have interacted with different items. So for example, you have this matrix of, let's say, explicit data of the form +1 or -1, which means a +1 means a thumbs up to a song or to a news article, and a -1 means a thumbs down. Or for example, it could be implicit feedback of the form, have you clicked on that, have you viewed that, and so on. So then based on this rating matrix, what you want to do is that basically you're trying to find out what is the predicted value for every entry of this matrix. And the way people have been doing that, for example, in the Netflix prize in 2006, was basically they're trying to say that this matrix, exactly because it's very sparse, because you have very few interactions of how different users have interacted with the different items, you are going to have a matrix which has a low rank. So basically, they're trying to approximate this matrix with the inner product of 2 latent factor matrices, U and V. So basically, this U matrix is the matrix of how different users, what are their latent preferences, what are the latent attributes. And then also V is for every item, Vj entry will be, it will be a d-dimensional vector where d is something very small, much smaller than the number of users or the number of the items, and represents what are the latent attributes of the items. And then the R hat, which is the predicted entries of the matrix, will be the UV transpose. So the main idea of this will be basically that you have this training data of how the different users have interacted with the different items. And you can see over there on the left, the green lines are basically positive entries, and the red lines are negative, meaning negative that I don't like something, and positive I like something. And now based on this training data, what you want to do is that you want to embed the users and the items to the same low dimensional space. So this, based on these embeddings, which will be based on these U and V latent factors, you will find out, for example, that which are the nearby items that I should recommend to a user. And so let's see, now we're going to see 3 main models that are using this latent factor-based approach. And I'm going to be talking about these models because then later I'm going to extend them in recommendation under constraints. Okay. So the probabilistic mass factorization model, which was a model which was developed by Selakutinov and Nee in 2007 for NIPS, basically says that they're trying to minimize this rating prediction loss, which is going to say that if, for example, you have data of the form how many stars every user has given to every movie, let's say 1 to 5 stars, it is going to try to predict whether a person is going to give 3 stars or 5 stars and so on. So that's the rating prediction loss. And also you have this regularization term. Now, if we go to the other model, it could be, this is the Bayesian personalized ranking model. So what this says is that instead of trying to have this problem as a rating prediction problem, you can actually model that as a ranking problem. So this is going to say that instead of trying to say that you're going to give 3 stars or 5 stars with the movie, you're going to try to rank properly all the items for the user. So basically, you're going to try to rank all the positively rated items for a user above the negatively rated items. And the way they're doing that is by maximizing for every user the probability of an item K, where K is positively rated, is ranked higher than the J item, which is a negatively rated item. And then because this probability is going to be given by the sigmoid function, so that it's between 0 and 1, of some parametric function of the user, the item K, and the item J. And if we do the derivations and so on, we're going to end up with this logistic loss function, and it's going to be a pairwise ranking loss. So this is the objective that Bayesian personalized ranking by Stephen Randall optimizes. Now, if we think about it, in some cases, instead of trying, let's say, to recommend movies or books, in a lot of recommendation systems, what they're trying to show you are what are the best restaurants, for example, you should go, or what are the best points of interest that you should go, or theme, attraction parks, and so on. So what this says is that you're going to have this checking data, which is going to, every entry now of the training matrix is going to have how many times these different users have visited the different items, or whether a user has visited an item, and so on. So what this brings us now is that every item is associated with this additional information, which is what is the latitude and longitude of every point of interest, of every item. So you have this physical geographical location that you can use, and you can use that in order to be able to give better recommendations. So now, the main idea behind all the methods that have been developed for point of interest location data for recommendations is that how can you capture the human mobility patterns? And the idea is that if a person has visited a point of interest, J, but then he has not visited the nearby point of interest, then this probably means that it's quite probable that he will not like the nearby point of interest. And he might like other point of interest, which might be far away. So the reason why we're saying this is because these matrices are very, very sparse, and you have only positive entries. So that's just implicit data. And so all the rest of the matrix is basically question marks. So you want to figure out if this question mark is indeed something that the user would not like, or if this is something that just the person didn't happen to know, or he didn't have time to go, and so on. So a very popular method for capturing this location data is geographical mass factorization, which again has this component of the inner product between two latent factors U and V, as we said before, for probabilistic mass factorization. But now also for every user, he's going to be associated with this activity area vector, and every item is going to be associated with an influence vector. So the activity area vector for a user is going to give us what is the probability of a user to visit every possible grid. So every activity area vector is going to be L-dimensional, and L are the number of the grids, capital L. So grids are, we're going to talk about them in the next slide, but basically the idea is that the whole world can be divided into evenly divided grids. Now, similarly, every item is going to be represented by this influence area vector. And so that tells us how much influence the point of interest J, let's say, has on the grid L. And now, so here we had, if you remember in the previous slide, we have U, we have V, we have X, and we have Y. So what we're going to say now is that basically how we're going to fix Y, and we're going to learn the different other parameters. So the Y, as we said, is the influence area vector, and it's going to have these L dimensions. So how do we get these L dimensions? So as we remember, every point of interest has a certain latitude-longitude coordinate. So then using some sort of a map projection, like the Mercator projection, you can get the tile coordinates for every item. And then using some method like kernel density estimation, you can compute what is the this distance of the point of interest of the grid. And so you can learn this influence matrix Y via kernel density estimation. And now based on that, you will fix Y and you will learn the other parameters U, V, and X by doing alternating minimization. Okay, so this has concluded the introductory part of the talk, which was some popular models for the problem of recommendation where we don't care about any other constraints. So now let's move to the main part of the talk, which is, let's imagine now that every item which is candidate for recommendation is going to be associated with a notion of capacity. So this is going to be based on some work that we have under review with Jaya and Professor Banerjee. So let's see why we will need, where this capacity constraint might actually appear. So let's consider the scenario that you have your perfectly good recommendation system. Let's say you have probabilistic factorization or Bayesian personalized ranking or whatever like is your favorite model is. But then let's imagine that this model will actually show to a vast majority of the population that uses the system that they should all go to the same show, let's say to the same Broadway show like Hamilton, something very good, very popular, a lot of people will like it. So then you can imagine that what will happen is that you will, because the theater has this fixed limited capacity, it is not going to be able to fit all these people. So you're going to end up with very large queues and people will be waiting, and probably this will lead to bad user experience because there could be some pretty good show around the corner that you could recommend to these people and they would enjoy the show. Now, another scenario could be that if, let's say, you are in this item recommendation system like Amazon or any other system that basically recommends to you different products that you could buy, let's say that this system has figured out to a large portion of the users that it should recommend the same product, let's say this skirt. So if that happens, and if that skirt in the inventory doesn't have a lot of copies, then what most of the user will see will be this out of stock message. Or for example, let's say in content delivery systems that have to recommend to you what should be the best video that you should watch, let's say in busy times like prime time or the Oscars, if it decides that, and in these times, you can imagine that there is already too much traffic. So now, if the system decides to also recommend to most of the users a viral video, then probably you will get some message like server overload. Or for example, if you have the system that recommends to you what should be the coffee shop that you should go, or what should be the theme attraction park that you should go in Disney, then if a lot of people are directed to the same thing, then again, you will end up with long queues, while there could be a pretty good place that people could be recommended to go at the corner. So this is the main motivation for, first of all, understanding where capacity constraints could be. And of course, you can also think of other scenarios like hotel recommendation and so on. And so now I'm going to introduce to you a very general sketch of how someone can actually tackle these capacity constraints. So the idea would be that, again, you want to minimize some recommendation loss, let's say rating prediction loss or ranking loss, as we did before. But then also you want to try to minimize something that captures by how much the capacities of the different items are violated. So, and you're going to have this trade-off parameter, alpha, let's say, that is going to do the trade-off between how much you care about the recommendation loss and how much you care about the capacity violation. And so you can very easily see that this basically is a multi-objective optimization problem. And also you will have some regularization term that will say that you don't want to overfit to your training data. Okay, so in order to be able to now formulate this capacity loss that we had in the previous slide, I will first need to introduce two main concepts. So the first is the concept of a user propensity. So what this means is that every user is going to be associated with a variable, pi, which is going to be a variable between 0 and 1 because it denotes the probability of a user to listen to the system, to basically follow the recommendation to the system. So that means that if a person is associated with a probability very high, that will mean that he usually tends to follow the recommendations. If it's very low, close to 0, then he usually doesn't listen to the system at all and he does whatever he wants. So one possible propensity definition could be that out of the total user AI and system interactions, you're measuring how many times the user actually followed the recommendation. Of course, you can imagine that this notion of propensity is much more general. So for example, the propensities of the users could vary with the time of the day, or could vary based on the users that the person is with. So for example, if a person is with his kids, then while the system could be giving a perfectly good recommendation for him, because the kids, this recommendation is not kid friendly, then probably he will not follow it. So his propensity at that point will become lower. Or for example, is varying with the time of the day. What it means is that, for example, I could tend to be pretty explorative during the evening so that I will have high propensity, but during my lunchtime, I'm pretty consistent that I want to always go to the same place. So then I will have very low propensity. Or for example, even how the interactions with the system go, my propensity could go high or low based on how engaged I am with the system. So these are all future things that someone could think of how can you actually estimate the propensity as a part of the model. Whereas here, what I'm just saying is that let's imagine that this user propensity vector is given to us somehow. Now, the second key concept that you're going to need is this notion of item capacities. So what this tells us is that every item is associated with this CJ variable, which is some number which is larger than 0. And basically what this says is that this could be, for example, the total number of the seats in some coffee shop or a restaurant or a cinema, or it could be the total number of visitors which are allowed at the same time to be in some place. So for example, that could hold for the theme attraction park, or it could be the total number of copies of the same item in the inventory. So this is something that is given to us from the data. And this is something that, of course, we need because there is this constraint of capacity. So we need to have this input of what every capacity of every point of interest is. So now, having all this information, we're ready now to compute what is the expected usage of a point of interest J. So the system, let's say whatever recommendation model you have, for now, we're going to be estimating the R hat ij, which is the predicted value of whether a person will like, user I will like item J, can be estimated this with different models. So in our case, we're going to be using the models that I talked about before, which is PMF or BPR or GOMF and so on. However, let's say, generally speaking, you have these predicted values for R, for the rating matrix. And now, if these were just 1 or 0, then what, and if all the people would actually follow the recommendation, meaning that their propensities would be 1, then the total number of visitors based on who the system recommended this point of interest would be the sum over all the users, R hat ij. However, every user, we said before, has a certain probability of listening to the recommendations. So we have to take that into account. So we have to multiply now every such thing with the propensity of the user. And also because the R hat ij, our predicted values, is not something which is binary, 0 or 1, we have to take the sigmoid function of the R hat ij in order to be the probability between 0 and 1. So now we have all the components ready for the expected usage. And now what we can do is that we can define what is the expected capacity violation. So this is going to say that I want to measure how many times the expected usage of the item is going to be larger than the capacity of the item. And then I take the average over all possible items. So in order to measure how many times, you have this indicator function, which is something which is non-convex. So you have to replace that with a convex function because we like these things in machine learning. And you want to have this function on the difference between the expected usage and the capacity. And you want to penalize more when the expected usage exceeds by more the capacity. So for example, there you can imagine a loss like exponential loss, logistic loss, hinge loss, and so on. However, for example, square loss will not be a good candidate because it will penalize both the cases where the expected usage is larger than the capacity, but also the case that we don't want when the capacity is larger than the usage, which is a good case. So here I'm just showing you some pictorial example that you have from your model this r hat ij, and now, as we said before, you want to put this r hat ij to be between 0 and 1, so you take the sigmoid. So these are the entries of the matrix that you see over there. But also you have these input vectors, which are the vectors of the propensity of the users, and also the vector of the capacity of the items. And so based on that, you can compute what is the expected usage, and then you can compute what is the capacity violation. And then if you, for every item, and then if you take the average, you can see, for example, in this example, I worked it out to be 0.3. So this is something that is not good. So ideally, we would want that to be 0. So basically, the system will try to minimize both the recommendation loss, as we said before, but also this notion of a convex capacity loss. Sorry. Okay. So now putting everything together, if, let's say, for the first objective, we use a rating prediction loss, as we have in PMF, and in the second objective, we have the capacity loss, but using as the convex surrogate the logistic loss, then this is going to be what our model is going to look like, its objective is going to look like. So now the unknowns are, again, the u's and the v's. And of course, we're going to minimize this objective using some method like stochastic gradient descent. And you're going to fix U and update V, you're going to fix V and update U, and you're going to alternate up until convergence. Also, if you remember in GeoMF, we had this variable of X, which is the activity area vector for every user. So here you will have as variables U, V, and X. So you will be using stochastic gradient descent for all three of these variables, as I show here. And of course, you can see that always we have this regularization term that prevents the overfitting. So that would make sure that when you turn into your test data, you will be able to generalize. And so in this paper we're also talking about other variants. So we have the CAP PMF model, we also have the CAP GMF model, but then if you, instead of having this rating prediction loss, you have this Bayesian personalized ranking loss, which, if you remember, is a pairwise ranking loss. You're going to turn up with having the CAP BPR. Or, for example, if you have also location, you will have CAP Geo BPR. And so right now I have described all the components of the model. And now we're ready to just show you some experiments for that. But before we go there, I just want to talk to you about the fact that the publicly available data that we have, like, for example, we use data like movie lens data, which capture what are the ratings that different users give different movies. And also we use point of interest data, which capture the check-ins of different users in different point of interest using data from Foursquare and Gowalla. However, all this data, and generally the publicly available recommendation data, do not give us the notion of capacity and propensity. So we had to have some way of actually inputting that to our model. Ideally, you would like to have them from some data, that they are giving these values to us. However, we tried to do the best that we could by saying that the propensities could be something that could be analogous to the usage. So essentially, in this data, what you have access to is how the different users have rated or have liked the different items. So now, using such an information, you can measure out of the total number of the items, how many are the observed ratings of the user. Or, for example, how many are the ratings that this user actually gave a +1, which means that he likes that. So that now will capture what is the propensity of the user. Or you can think about it as saying that the propensities can be irrespective of usage. So, for example, you can just, put all the propensities to be within some range. So using some linear function. So that's the possible propensity definitions. But now for capacities, which is even more important, we thought about 3 different cases that we think are exhaustive. So the first case could be that the capacity are analogous to usage. And this is something that actually is very relevant to supply and demand law, which basically says that the more people actually want something, the more copies of this something will be in the data. So we have different notions of capacities analogous to usage. Also, it could be the case that the capacities could be completely irrespective of usage. So you can have, imagine, uniform capacities and so on. Or you can also have capacities which are reversely proportional to usage. And what this would tell us would be that items which are in high demand, it will be like elite. So you would have low capacities for them. So, for example, we have this notion of before we had binning, but now we will have the reverse binning, meaning that these items that had very low usage, they will be assigned to a very large capacity. And items which have very large usage, they will have very small capacity. So these are the three different definitions that we use for capacities. And now we're ready to ask different research questions. So the first one would be just to make sure, it would be just a sanity check, just to make sure that by varying this trade-off parameter of how do you do between the rating prediction and the capacity loss, whether actually the results are as expected. So you see over there for the two different data sets, for the two different movie data sets, that as you increase this alpha parameter, you get better in terms, I'm sorry, it goes very fast, the slide. Okay, so it gets better in terms of capacity loss as expected. And in terms of RMSE, which is the rating prediction loss, it becomes worse because it becomes higher. Whereas in reality, we want it to be as close to zero as possible. Also, in the point of interest location data, you can see that in the Foursquare data and the Gohala data, where you have this point of interest, so we use this CAP GOMF, you can see again that the capacity loss is going down, which is this purple bars, but however, you can see that the rating prediction loss is going up, which is as expected. So now if we move to, instead of having this rating prediction loss, if you have this pairwise ranking loss, as we had in BPR, we also tried to see whether we will have this expected trade-off. But what happens is that, for example, you can see that although the capacity loss indeed goes down as you increase A, the rating prediction loss, the pairwise ranking loss, it actually doesn't change much. So sometimes it goes a little bit down, sometimes it goes a little bit up, and so on. So that was interesting. And for that experiment, we were using the capacities which are analogous to usage. So we wanted to plot what happens. So just in training data, for the two data sets here that we show, MovieLens and Foursquare, you can see that even when we vary the trade-off, and let's say we have a trade-off parameter of 1, meaning that we don't even optimize for a pairwise ranking loss, you can see that actually our model is able to optimize for this pairwise loss. So basically what this says is that by using capacities which are analogous to usage, it's sort of like a sufficient statistic of being able to recover what is the correct pairwise ranking accuracy. So then we wanted to do this experiment where instead of having these capacities which are analogous to usage, we can have capacities which are reversely proportional to usage. And if we do that, then the two objectives are indeed competitive. So here we can get this expected trade-off. So here I'm just showing this different sensitivity analysis. Let's not go through that. And then something which is also important is what would be the effect of the top-end recommendations. So here what I'm showing to you is that while in some data, when you vary the trade-off and you make the trade-off parameter larger, you can get worse recommendations. However, for example, in Foursquare data sets, you can get better recommendation. And we have some analysis that I'm not going to go through now because I want to talk to you a little bit about some other kind of constraints. So this part just concluded the capacity constraints, but also you can think of that you can have other types of constraints like space. So for that, I'm going to just give you a glimpse of some other paper that we had done in the past with my advisor. So the idea there is that we're living in this world where at the beginning people were checking their recommendations, in their computer screen, but right now everyone's checking their recommendations in their phone, in the tablet, or even, in an Apple Watch. So that means that the actual space where the recommendations could go is very, very small. So that means that what I can do is that I want to present the very top recommendations to be good, because if I don't, then that will mean that this person will not actually even see them. So essentially, if you remember the BPR objective, the pairwise ranking one, although it does pose a problem as a ranking problem instead of a rating prediction one, what it doesn't do is that it doesn't play more emphasis on the top of the list. So what we did in this work, and also what other works have done, is that they have explored this connection between the recommendation literature and the learning to rank literature. And what the connection is that the user is the query, and the different items that you want to recommend to this user, these are sort of the documents pertinent to the query. So basically all these things that are in the learning to rank literature, like all these metrics and so on, they're applicable for recommendation. So one such thing was this ranking with a push objective, which was a paper by Cynthia Rudin, very nicely done paper. And the idea is that for a given user, if you have access to some scoring function, then you're able to see, you're able to rank these items for the user. And then based on this ranking list, you can see whether every item is positively rated or negatively rated. So then for every negatively rated item, which is a non-relevant item, you can measure how many are the items which are below this. So this is a number that you want to be small because you don't want to have relevant items underneath non-relevant ones. And also you want to penalize the larger heights because this would correspond to non-relevant items being closer to the top of the recommendation list. And this is something that you don't want, as we said before, because, for example, in your Apple Watch, you don't want to have a non-relevant recommendation to be shown to you. So in order to do that, we have this push function, which is this convex increasing function on the heights. And we also, again, we're using this latent factor approach in order to be able essentially to compute the scoring function instead of saying that the scoring function is given to us. And also we have this convex surrogate of the indicator function, which is found in the heights. And we use, for example, the logistic loss and so on. And so if you put everything together, I'm going very fast right now just to give you the idea of that. What I'm going to show you is that just, again, you have this variables, the u's and the v's, and you're going to do stochastic gradient updates. And also you can have different kind of objective functions. So instead of saying for the push function that it's, let's say, the p norm of the vector of the heights, it could be something else. So for example, it could be the infinity norm of the vector of the heights and so on. So you want something which is convex increasing. And we just showed in the experiments that treating the recommendation as a top ranking problem actually is much better compared to, let's say, having the PMF model of a rating prediction. And by using these latent factors, actually we're better, we were outperforming the learning to rank solution of building a separate model per user as expected. So now I just want to give you these final ideas of other kind of constraints which are out there in real-world recommendation systems. So one such constraint is a time constraint. So essentially, you can imagine that you can have all these low latency applications where the system should tell to the user which road it should take based on the dynamic traffic or accidents which would be happening and so on. Or for example, you type something in Google and you want to get this personalized result. This is something which would happen immediately because of good user experience or because it's a time critical application. So again, you can also think time in different sense. So for example, if I'm recommending to you different restaurants that you should go, so some restaurants could be closed in some specific time, whereas some other restaurant could be open today. So essentially, when my favorite restaurant is open today, I should be able to recommend that to the user. However, if this restaurant is closed today, I should be recommending to him the best next thing. Another kind of a constraint would be a human cognitive load. So the main thing that you should think of in recommendations is that whenever you're giving a recommendation, you're giving that to a user. So the way you present these recommendations to the user actually matter a lot because, for example, how you present to them as a list or as a grid, or for example, how do you elicit his preferences by asking questions? Are his questions absolute or relative and so on? This would actually mean that this user should put more or less human effort. And of course, you want something which is as easy for the user as possible. So there is work which is essentially work on human decision-making and also human-computer interaction. And this is very relevant. And so just to conclude, I want to say that we talked about capacity constraints, which are present in real-world recommendation scenarios like points of interest, or for example, even for product recommendations. We talk a little bit about size and space constraints, which basically translates to caring about the top of the recommendation list. So that's a top-end recommendation problem. And of course, there are so many other future directions like time constraints or cognitive constraints, as I very briefly talked in the end. And also you can think of that all the different factors, like for example, serendipity or novelty, or making sure that if you are in a news recommendation system, you just give to the person a fair view of the world. So mainly not having this filter bubble and so on. All this can be actually captured as constraints that the system should actually try to minimize, to respect, while at the same time it gives good recommendations. So with that, I want to conclude, and I will go in the chat and see what we're saying. Great. So we have 2 questions. So Charlie asks, what are the biggest problems with constrained interactive settings? Okay, great. So essentially this whole talk was about constrained offline recommendation. So I talked about this idea that essentially this data of how different users interact with the different items, this is something which is given to us somehow magically. And then you build this offline model, and you're trying to, you're essentially saying that this model would be doing well in also future data. However, also a lot of work that I have been doing is in interactive recommendation, mainly saying that how do you capture recommendation as an interactive learning problem? And the idea there is that you would have to dynamically update all the different parameters of, let's say the users or the items and so on. But also you want to measure this exploration exploitation trade-off by basically saying that if I don't know a lot of things about the user, I should explore a little bit to learn his preferences better. But then as soon as I have figured him out, I want to also exploit so that I give him the best possible recommendations based on what I have learned about him so far. So now you can very easily imagine that, as you said, interactive constraint settings is something which is essential. So essentially, in interactive settings, mainly people in Bandits, for example, for recommendation, mainly people have been trying to optimize different notions of regrets or rewards, which are based on, let's say, click-through rate, or how many clicks this system got on average by the different users. However, if you also take into account the constraints, like, for example, capacities, or diversity, or time, or different things that I said so far. So mainly, if you incorporate this notion of constraints in the reward structure, then you will be able to build interactive constraint systems. So I'm not sure if that answers your question. Let me know in the chat if it does. And also just wanted to say that it's a very interesting future work to basically, so this offline model, let's say for capacity constraints, it doesn't take into account at all the time. So you can think about it that it's a very natural thing to actually build a dynamic model of recommendation under capacity constraints, because the different users who go to the different, let's say, theme attraction parks and so on, they will not essentially only come from the recommendation model, but they're also going to come because people decided on their own or based on some other system that they should go there. So essentially, there should be a way of actually trying to estimate what is the queuing delay at that point, or for example, to estimate dynamically how many are the number of people who are going somewhere, or how many are the number of people who are waiting in the queue, and so on. So I hope that answers. So now let's go to the next question. So Misam says, to possible cons of the model, if you do not always recommend the best possible item to the user loses confidence in the model. By not letting items run out of capacity, user press signals to other parts of the system to order more of certain items. How would you address this? So let me try to understand the question. So I see. So essentially, you are talking about this idea of it could be the best thing that, if let's say we know that the best thing that I want to recommend to a person would be that this Starbucks around the corner, then if I don't recommend to this person, then he would probably feel like this is not a good recommendation system. So that's where essentially the user propensity to listen comes in. So essentially, if you know that this person is actually listening a lot to my recommendations, what this will mean is that this system is going to say that since this person is going to follow my recommendation, I know that if, for example, I recommend to him the favorite place, or if I recommend to him, this place which is the next best thing, which doesn't have this long queue, then probably he will follow. So we want to have this trade-off between having good recommendations. So I'm not saying that the recommendation should be bad, but at the same time, you should also pay attention to the capacities. So what I didn't show you for the constraint of time, let me just go into the slide, was that essentially in our model, if, for example, let me just see if we have it here. So what we found is that just by increasing the trade-off parameter alpha, it doesn't always mean that the recommendations are going to get worse. In reality, if, for example, you have this pairwise ranking objective of BPR, and at the same time you're doing the capacity constraints, then, and if you have capacities which are proportional to usage, you can see that as you increase the trade-off parameter alpha, you're going to become better in terms of weighted average precision on top. So, and here this baseline that I have is basically some sort of a post-processing baseline which says that let's say I just have my perfect recommendation system, let's say PMF or BPR or your favorite model, which does R hat. So that would essentially give the favorite thing to a person, right? Because it would give the best fit. However, now you know that every item has a fixed capacity. So you can sort the users essentially for every item. You can sort the users based on the predicted scores, and you can present this item to the top CJ users, where CJ is the capacity of this item J. So now, and then based on that, you can show the top and recommendation list per user. So now you can see, you can imagine that this strategy will actually have zero capacity loss, exactly because you just show the item to only the people who can fit in this place. However, so here you can get a hit in terms of average precision on top, because exactly in that way you don't optimize directly. Although the original R-hat was trying to optimize recommendation performance, because of the fact that you tried to respect the constraints, it took a hit. However, in our case, when we have these actual capacities, you can see that as we increase the trade-off parameter, you can actually get also better in terms of the capacity loss, but also in terms of the average precision on top, which measures the recommendation loss. So this, however, doesn't always happen. So it depends on the notion of the capacity. So for example, if you have a ranking loss, but then the capacities are reversely proportional to usage, then as you said, in that case, you will get worse recommendations, which would actually, might potentially deteriorate the user experience. Or for example, in the rating prediction loss, we had a different story. So essentially it was saying that when you have capacities which are proportional or irrespective to usage, then our framework would be better than the baseline. Whereas in the opposite case, it wouldn't be. So what I wanted to say by that is that basically it doesn't always mean that when you're trying to optimize for these two objectives, that your recommendation accuracy is going to go down. So essentially, if someone would be to deploy the system, he should pay attention to understanding whether the capacities are analogous to usage or inversely proportional, or whether you care about rating prediction loss or pairwise loss, or even some other, let's say, top ranking loss. And based on that, he should see whether that would deteriorate the user experience or not. Okay, so let me just go to the new question. So why do you need to incorporate the constraints in the deep learning model? How about, oh, that's great. How about some post-processing constraint? For example, recommend only 20. That's amazing. Okay, I hadn't seen this comment. So I think I just answered this by showing you this baseline that essentially, it was a post-processing baseline, as I said quickly. Let me just elaborate a little bit. So basically, the idea would be that you get from your favorite recommendation system the recommendations, but then you only care about for every item, you sort the users based on the score, and you recommend this item to the top users, so that if an item's J capacity is CJ, then you just show to these CJ users. So then you will have zero capacity loss as you want. However, you might get a hit in the recommendation performance. Okay, let's go to some other part of the question. By not letting items run out of capacity, you suppress signals to other parts of the system to order more of certain items. I'm not sure I understand. So what do you mean, Misam, by suppressing signals to other parts of the system? So essentially, if I understood the question, I think again you're trying to say that by incorporating this notion of a constraint, right? Right. So you're constraining the items, not going out of capacity. Yeah. So basically, you are trying to say that the expected usage of every item should be within this capacity constraint. That's correct. But then, exactly because you have the same variables U and V, the latent factors of the users and the latent factors of the items, you are optimizing at the same time both for the rating prediction or the pairwise ranking objective and the capacity loss objective. So because you're learning both of them at the same time, you are trying to, the signals, if I'm trying to understand correctly, the signals are basically saying they're trying to both understand what every user's favorite items are, but also whether these items will run out of capacity or not. But I'm not sure if I'm answering your question. Let me know if you want further explanation. So it's true, it might happen that the certain item that you're pretty sure that this user will like, in this case, it might be that if you recommend to some people something which is not their favorite item. But however, even if you recommend it to them, their favorite item, and they go there, and then they experience these long queues or they see this out of stock message, then the whole point is that their user experience will be deteriorated, because if we say that, let's say that these people have very high propensity, so they tend to listen to the system, so they will be happy first of all with their recommendation, because they will say, okay, the system understands me and knows, for example, that I like this restaurant a lot or this product or so on. However, then they will see this out of stock message or the long queues and so on. So basically, what you can do is that you can understand, for example, I'm not doing it explicitly in this model, but if you want to extend it, you could say that I'm going to target more the people who have higher propensities. And so for these people, let's say, I want to present to them, there are two things that you could do. Either you could say that for these people, I would present the next best thing so that we know that they will go there. So these places will not have the long queues and so on. So they will not have a bad user experience. But of course, what we recommend to them would be something good because it's given by the UV transpose thing. However, the people who are not, maybe they will not follow the recommendation, we're going to put them in some other place and so on. So essentially, you can use this notion of a propensity in order to understand who are the people that you should target and so on. Yeah, it would be great. So if you need, if you need any further explanation, you can send me an email, or maybe I can post something in the blog later and so on. Thank you so much, guys, for watching. It was amazing to also talk again in AI with the best. So if you have any other questions, feel free to contact me. I can just post there what my email is. And I just want to say thank you to my collaborators as well, because as I said, this is joint work with my advisor and with Jaya. So yeah, thank you so much. Have a great day.